well. Welcome, everyone. So we start talking about proofs, and we're going to go over different types of proofs for universal statement, existential statement, and in general, using a statement and applying different types of proofs. But before doing that, here's a question. Why do we need logic? Why do you have to verify a statement being true, false, understand the validity of a statement? Think about it this way. How do we interact? We talk to each other through a common language, English. English is not my first language. I had to learn the words, the letters. Okay, then I learned the grammar, and that way I can form statements in English and speak to you. You understand me, and if I change those statements, it might not make any sense. Very well. So how do we interact when we have AI, artificial intelligence? We have to start by having some fundamentals, all right? The fundamentals, we need to have the very basics of that language to be able to interact. We need mathematical logic in the heart of those fundamentals. Logic helps us to define statements, which are declarations, true, false. We use and or negation, implication by conditional to form compound statements. Well, okay. We have some operators: addition, subtraction, multiplication, well, division, finding the remainder, mod operator, div operator, raise to, so plus some operators. We are interested in analyzing these compound statements, and if we just add those operators, having some statements related to computations, when those statements are true, when they are false. Again, the building block is logic. How do we think, and how do we interpret that thinking into machine? Well, okay, so this is a new language for us, all right? We're going to use this new language, this new grammar, these new letters, building blocks to interact with machines. What do we need? We need cognitive science. So this is our fundamental. Cognitive science. We need cognitive psychologists, experts in brain that actually help us to take a look at the mapping of the mind, our human cognition, how to map human mind. So this is the easiest way for us to take this language and make it work that we understand it and machine understand it. For example, they use cognitive science, brain science to talk about perceptron. Perceptron. Okay, they model perceptron. Again, they have the language, they have cognitive science that go back and forth. Perceptron. Well, they use perceptron to define neural networks, how our brain works, how our mind perceive different things and interpret that, and then we analyze it using logic. This is one of the examples in many neural networks. And if we add more layers, we are constructing something that we call convolutional neural networks. This guy has applications everywhere. They use neural networks in machine learning and convolutional neural network in deep learning. Again, we have a language. We define this language in this course, in this grid map. We add more complicated, complex statements that are related to computations. This is eventually the thing that we want our algorithms and machines deal for us. But eventually, we need to have a way, a method interacting with our machines. Perfect. So now, in order to analyze complex, complicated statements, we human mathematicians, computer scientists, we come up with different methods of proving or disproving statements. This is the whole concept and the method that we're going to deal with in chapter 4. Very well. So let's get back to the fundamentals. Let me just categorize different methods of proofs, these proofs that we're going to discuss in chapter 4. Well, for a statement, suppose you have a statement, you either have a universal statement, or you have existential statement, or in general, some statements. If you have a universal statement, to prove a universal statement, we take a look at the domain. So in the first case, if the domain is finite, it means that you have to take each element in the domain and check to see if that predicate is true for that statement. So if the domain is finite, we check for each element. Sometimes they call it exhaustion method. If the domain is not finite, then what are we going to do? One of the methods is to use direct definition. We use definition to prove the statement. Well, so far we tried to prove. Now I expect you to ask, what if I already know a universal statement is false? How do I prove that? So this is for proof. For a universal statement, if you have the case to disprove, a universal statement, you need to find a counter example. We find a counter example. So again, we have universal statement. So far, two ways to prove a universal statement. If the domain is finite, you just check for each element. If the domain is not finite, we use the definition to prove. Okay, we check to see what definition do we have. Do we have a definition of even number? Do we have a definition of prime? Do we have a definition of composite? Or later on, we're going to talk about divisibility. If the question says, hey, disprove the universal statement, your job is to find one example that makes the statement a false statement. We call it a counter example. What if we have an existential statement? Existential statement. Okay, existential statement sometimes is super easy. To prove an existential statement, it means that you need to find at least one number that satisfies that condition. It's super easy, pretty straightforward. We need to find one element, one number that satisfies that statement. That makes the statement true. How do we disprove? Disprove. To disprove. Very well. The negation of existential statement is a universal statement. So it means that we need to show that for any arbitrarily taken element, that statement is false. We need to show that. For a random element, arbitrarily taken, it cannot be a specific number or value. It's a no-no. So we need to show that for a random element, the statement is false. Pretty straightforward. Universal statement, existential statement. Sometimes we have statements that are not in the category of being universal or existential. In this case, for a statement, we can apply two different indirect proof methods. The first one is called proof by contradiction. So in this case, we assume the conclusion is wrong and we reach to a contradiction. In this method, we assume the conclusion is wrong and we get to a contradiction. So we usually denote contradiction by this symbol, contradiction. So proof by contradiction. This is the name of this method. It's not a universal statement, it's not an existential statement. Sometimes it works for those methods as well. Very well. Another method is called proof by contraposition. Proof by contraposition. This is usually work when we have implication. Well, In this case, you already know what is contrapositive. Instead of proving P, then Q, instead of proving P, then Q, we prove not Q, then not Q. So this is the general that we need to start thinking how to prove or disprove different types of statements. Very well. So, okay, we talked about different types of proofs. Give us an example. Sure, let us begin. There we go. Example. The example, which is on page 4, 4.1, page 4. Okay, in this example, question says, for any integer like x, if x is even, then x squared is even. Okay, perfect. So we have a universal statement, am I right? We have a hypothesis, and then we have a conclusion. Here you can say that we have a universal statement. Note that the domain is Z, the domain is not countable. The domain is not countable. So it means that we cannot take values from Z and check each one of them. It's impossible. We cannot take all elements from Z and check the statement. So which method do you prefer? Do you prefer to use direct proof? Would you like to use proof by contradiction? Or would you like to use proof by contraposition? One of them is the best choice, and for some others, we have to take a look at it, try to use either of these methods. Sometimes it's solved very fast, some other times it doesn't give us a nice answer. So we're going to start by using the direct proof. Direct proof, so remember that, recall. Since you're using direct proof, you need to have the definition, an integer. An integer like n is even if and only if n can be written as the double of another integer. There is another integer like k such that n is 2k. Okay, this is the definition that we learned before, and we want to use the direct proof. Direct proof says, okay, you have your random integer, you cannot specify what x is. That is a no-no. It's a universal statement, it works for all arbitrary numbers. X is even. Since x is even, it means that there is an integer like k such that x is 2k. The conclusion says now x squared is even. X squared is equal to 4k squared, which can be written as 2 times 2k squared. Well, k is an integer. K squared is an integer. 2 times the integer is also an integer. Since we have to all add these little details. Since 2k squared is an integer, x squared can be written as 2 times L, let's call it L for simplicity to write it in nice compact form, and x squared is an even number. So we proved by definition. Okay, at the end of your proof, you can use this little box with a dot in it to show that, hey, you're done with your proof. Proof by contradiction. Let us try this method, then try proof by contraposition. Proof by contradiction says, okay, suppose not. Suppose the conclusion is not correct. What's the meaning of that? It means that the conclusion x squared is not even. This is the conclusion. Okay, conclusion, it's not even. Since it's not even, it's odd. So x squared is 2k plus 1. So where can I go after this step? What is the next step? Suppose I get rid of exponent 2. Suppose I write x as plus minus square root of 2k plus 1. But this guy doesn't give me anything to work with. I have square root. This square root makes this number might be irrational number. So since I don't have integer, I cannot work with my hypothesis. So this is not helpful. Not helpful. Well, so I'm not going to use proof by contradiction because it's not helpful. What if we use proof by contraposition? So this is not helpful. I'm going to just cross it off. Proof by contraposition says, instead of proving P then Q, we need to prove not Q then not P. Okay, not Q then not P. This is my P, this is my Q. It means that I need to show that for any integer like z, if x squared is not even, then my hypothesis, the negation of my hypothesis, then x is not even. Then x is not even. Okay, how do I prove this? If x squared is not even, then x is not even. So let me try direct proof. X squared is not even. What's the meaning of that? It means that x squared is what? 2k plus 1. So if x squared is equal to 2k plus 1, again, if I get rid of the exponent 2, x is plus minus square root of 2k plus 1. Again, I ended up with square root, and I don't know if I have a rational number, integer. It makes the rest of the proof to be unstopped. So it's not going to be helpful. It's not helpful. So in this case, the best method is direct proof. In this example, the best method is direct proof. Example, we are on page 5. It says, well, show that the following statement is false. Show that the statement is false. Okay, disproving something. What is the statement? There is a positive integer. There is a positive integer like n such that n squared plus 3n plus 2 is prime. Because the definition of being prime, being composite, they say that we call for you an integer. Like n is prime if and only if that integer is absolutely greater than 1, and if you write n as the multiplication of two other numbers, r times s, we have n equals to r, or n equals to s. Otherwise, we say it is composite. Officially, we write it this way. We call an integer like n is composite if and only if n is greater than 1, and if you can write n as the multiplication to other numbers, we have this condition. R is between 1 and n, and also s is in between 1 and n. Well, so direct proof contradiction, method of contradiction, contraposition doesn't work here. Contraposition is not working here. Why is that? Remember that we said contraposition is for the case that we have not Q, then not P, for an implication. We don't have implication here. It says there is a positive integer such that you have this condition, no implication. So this guy doesn't work. Direct proof. There is a positive integer that n squared plus 3n plus 2 is prime. Okay. What is that integer? If I want to prove this statement, I need to show that I have an integer. What is that integer? What is the integer that makes n squared plus 3n plus 2 prime. Very well. So since we know that we can falsify this statement, we already know that this statement is not true. It means that we cannot find that integer. So what is our approach? Our approach is we have a statement n squared plus 3n, we have an expression n squared plus 3n plus 2. Since n squared plus 3n plus 2 can be factored into n plus 2 times n plus 1, well, this is a factorization of an expression into two other factors. I can easily analyze n plus 2 and n plus 1. Why is that? N is a positive integer. Since n is a positive integer, n is greater than or equal to 1, equal to 0. So n is greater than equal to 1. All right. So n plus 2 is definitely greater than 1. At the same time, n plus 2 is a factor of n squared plus 3n plus 2. So it definitely is less than n squared plus 3n plus 2 by algebra. Also, for the same factor, n plus 1, n is greater than equals to 1 because it's a positive integer, and n plus 1 is definitely greater than 1. And since n plus 1 is a factor of n squared plus 3n plus 2, it is less than n squared plus 3n plus 2, again by algebra. But hey, we already defined a composite number. A composite number is a number greater than 1, which if you can write it in factored form, those factors are greater than 1, less than the number. So as you can see, these two factors are greater than 1 and less than the expression or eventually our number. So you write by definition of a composite number, n squared plus 3n plus 2 cannot be prime. If you take any random, arbitrarily taken integer, positive integer, this guy cannot be prime. Next example. So the first example says, is 10 divided by 3 a rational number? B, is -5 divided by 39 a rational number? C, is 0.281 a rational number? Is it rational? D, how about 7? Is 7 a rational number? E, well, is 0 a rational number? F, how about 2 over 0? Do we have a rational number? What if I flip this? G, is, I'm sorry, what if I change this to the complement? 2 over 0 is irrational. And finally, is we have 0.12, 12, 12, 12. So 12 is repeated non-stop, a rational number. Isn't that fun? Yes, it is cool, very cool. So we try to find, a repeating pattern, something that actually help us to work with these types of numbers. Perfect. So let's see, what do I have here for you? Some properties of rational numbers. And then just going a quick introduction into divisibility. So, is this number a rational number? Well, we're going to do a little trick. We're going to take x to be equal to this number. We're going to multiply both sides by 100, 100x. It means that we just shift this decimal 2 places to the other side. So 12.1212 and 12 is repeated. Now you're subtracting 100x and x. You're subtracting x from 100x. So we get 100x minus x equals to, well, 12.121212 minus 0.121212. So 99x is equal to 12. It's like subtracting 12.80 and 0.80. The outcome is 12. So x is equal to 12 divided by 99, which is a rational number. Very well. So let us continue. 4.2. Let us move on to page 2. Zero product property. Zero product property. You already know this property. You already use this property. You know that if you have 2 non-zero integers and multiply them together, the outcome is non-zero. If 2 integers are non-zero, then their product or their multiplication, is not 0. So we have a name for this property and we call it zero product property. You saw this theorem before. Just noting these down, any integer is actually a rational number. Any integer is rational. In chapter 1, we mentioned that we start by having n as natural number set, counting numbers, then we expand the idea to adding 0 and having whole number system. Then, since we don't have negatives, we expand this into integers. We expand integers, we don't have fractions, into rationals, Q. And then we say that, okay, we have some rationals, we have some numbers that are not rationals, like square root of 2, pi, square root of 5, and we define the complement of rationals as irrationals. And all of these are included in a larger set that we call reals. Okay, and at the same time, we know that reals are a subset of complex numbers. Here we go. Complex numbers. So as you can see, by looking at the Venn diagram, if you want to take it more formal way, N is a subset of W, subset of Z, subset of Q, and so on. So any integer, for any integer, that integer is a rational, but the opposite is not correct. So note that the opposite is not correct. It means that we have rationals that are not integers. Aha. There is this one. So it's not enclosing. It should be just right here. The combination of these two, the union between Q and QC is R. So R is Q union with QC. And Q intersection with QC is empty. Perfect. So this is an example on page 3. If A is any even integer, so example. This example says, let A be even, be an even integer, and then B is any odd integer. Any odd integer. Question says, show that A squared plus B squared, show that A squared plus B squared plus 1 divided by 2 is an integer. Belongs to Z. It says for sure show that it is definitely an integer. Okay. Which method do you prefer to use? Direct proof? Contradiction? Contraposition? Which one is your preferred method? Okay, we want to show that this guy is an integer. Well, let us use the definitions. Okay. It says A is even. So there is an integer like K such that A is 2K, and you have another integer like L such that B is 2K plus 1, because B is any odd integer. Let's do a little bit of algebra. Algebra says on the numerator I have A squared, so I'm going to square 2K. 2K squared. Then B is also squared. I have 2K plus 1 squared plus 1 divided by 2. Very well. So I have 4K squared plus 4K squared plus 4K plus 1 divided by 2. I have 8K squared plus 4K plus 2 divided by 2, which can be simplified into 4K squared plus 2K plus 1. But let me just leave this as L. I don't want to make you confused about these. It's easier not to combine them. L. So here we have 2K squared plus 2L plus 2L plus 1. So K is an integer. 2K squared is an integer, so it belongs to Z. 2L squared is another integer, belongs to Z. This square is also an integer, plus 1 is going to be another integer. The sum of integers, we already know that is an integer. So this is going to be just an integer. We're going to actually start 4.3 officially on Wednesday. I'm just going to go over 2 important definitions that we're going to use later in 4.3 to prove things. So first of all, we're going to talk about an important theorem that we call Quotient Remainder theorem. Quotient Remainder theorem. This theorem says, well, suppose n is any integer. Let n be an integer. Let d be an integer which is not actually negative. Let d be a positive integer. We can find 2 other numbers. We can find 2 unique numbers. We can find 2 unique numbers, Q and R, such that n can be written as d times Q plus R, and R is sandwiched between 0 and D. Q is called the quotient, and R is called the remainder. Quotient and R is the remainder. Very well. You've used this many times. For example, think about n as 54 and d be equals to 4. This is an integer, this is another integer, non-negative integer. N can be written as D times Q plus R. 54 can be written as 4 times a quotient plus a remainder. Just doing the division. It's nothing but the division. So 54 is equal to 4 times 13 plus 2. And note that 2 is in between 0 and D, which is this theorem, which is very important, is called Quotient Remainder theorem. After quotient remainder theorem, what comes along is divisibility. So if the remainder is equal to 0, we say that D divides N, or N is a multiple of D. So we say that if N and D are integers and D is not 0, if N and D are integers, note that D cannot be equal to 0. We write D a vertical line, N, and we read it as D divides N, D divides N, N is a multiple of D, multiple of D. D is a factor of N if and only if we can find an integer. There is an integer like K such that N is D times K. Divisibility, the definition of divisibility. If we have two integers and the other integer, we're going to go over that later, D is less than or equals to N. It's our Wednesday topic to prove some statements. D divides N, or N is a multiple of D. D is a factor of N if and only if you can find another integer such that N is equal to D times K.